Okay. Well, if you're ready to go, Sasha,
Yeah.
we're happy to have Sasha back for lecture 2, where he's going to tell us about homogeneous varieties. Thank you.
Yes, thank you very much. Yesterday we discussed exceptional collections in general, and since our subject is exceptional collections on homogeneous varieties, now we have to switch to homogeneous varieties. So I hope to have time today to give you a brief survey of homogeneous varieties, and then I will tell what is known about exceptional collections on homogeneous varieties. Okay, so for us, homogeneous varieties are actually compact homogeneous varieties. And this means that these are varieties that can be, these are homogeneous varieties of simple algebraic groups that can be represented as quotients G mod P, where G is a simple algebraic group, and P in G is a parabolic subgroup. And parabolic means that it contains a barrel subgroup. And the good thing is that simple algebraic groups have been classified, and I will going to tell you some bits of the classification. Also, every simple algebraic group has a unique up to conjugacy barrel subgroup, and the conjugacy classes of parabolic subgroups are also classified, and all this classification is given in terms of Dynkin diagrams. So all this is classified by means of Dynkin diagrams. And here you can see the list of all possible Dynkin diagrams. So there are actually 4 series: AN, BN, CN, and DN. So these are series. And there are 5 exceptional cases. So these series are usually called classical series. You will see in a minute, and the reason for this is that the corresponding algebraic groups have a very classical description. And groups in exceptional series, they also can be described more or less explicitly, but these descriptions are not as convenient and not as well understood as the classical cases. So let me also mention that the index in all this notation, index n in the first 4 cases, and index 6, 7, 8, 4, and 2 in the exceptional cases, corresponds to the number of vertices in the diagram. And the diagrams are written here. So AN is just a chain of n vertices. BN is a chain of n vertices, but one of the edges is doubled, and there is also this inequality sign on this doubled edge, which essentially tells you that the data corresponding to the first n-1 vertices, and this data is what is called simple roots, they have bigger length than the simple root corresponding to the last vertex. The case Cn is very similar. The only difference is that this time the inequality sign on the last doubled edge is in the opposite direction, which means that there are n-1 short roots and 1 long root. In the case Dn, instead of a chain of vertices, we have a kind of fork at the end, but still altogether there are n vertices and all roots have the same length. The Dynkin types E6, E7, and E8 have this particular form. There are no double edges here, so all roots have the same length. For type F4, we have 2 long roots and 2 short roots. And for type G2, we have 1 short root and 1 long root. And this time the edge is a triple edge. It is not a double edge. And double edge means that the length of the long roots divided by the length of the short roots is the square of 2, the square root of 2. And in the G2 case, the ratio is the square root of 3. So the multiplicity of the edge corresponds to this ratio. Also, let me just tell you that AN, DN, and EN Dynkin types are called simply laced. This means that all edges have multiplicity 1. You don't have double or triple edges in this case. And the other types, BN, CN, F4, and G2 are not simply laced. Non-simply laced, because they have double or triple edges. Okay, so the classification tells you more or less that every simple algebraic group corresponds to one of these Dynkin diagram. But there is a small ambiguity in the choice of a group corresponding to a diagram. Actually, all the groups of a given Dynkin type may differ by a finite subgroup. So let me tell you some examples. So in fact, in each of Dynkin types, there are 2 extremal cases of groups. So one is called simply connected. There is a simply connected group. There is also a joint group, and there are some intermediate groups. So let me tell you how this looks in the classical cases. So in the type AN, the simply connected group of type AN is just SL n plus 1. Use this notation. And the adjoint group of this type is PG L n plus 1. And intermediate groups have the form SLN plus 1 mod mu D, where D divides n plus 1. So, and mu D is considered as the group of roots of unity of order D, which sit inside the group SL as diagonal matrices with roots of unity at the diagonal. Of course, if you take D equal to n plus 1, you will get PGL. If you take D equal to 1, you get SL itself, but there are also intermediate possibilities. Okay, so that's the first case. So in the case of the group Bn, so the adjoint group is the group SO of 2n plus 1. So it is a special orthogonal group of 2n plus 1 by 2n plus 1 matrices, so matrices of odd size, and the corresponding simply connected group, which is a double covering of this group, is called spin 2n plus 1. And in this case, there are no intermediate groups just because this is a degree 2 covering, and so there is no room for groups between these two. So in the case Cn, it's easier to describe the simply connected group, which is just symplectic group of 2n by 2n matrices. And the adjoint group is, we can say that this is, maybe let me write it as sp2n quotient by plus minus 1. So it's similar to the relation of the SL and PGL. And again, the simply connected group covers the adjoint group. The covering degree is 2, so again there is no room for intermediate groups. So this is the case Cn, and in the case Dn, in this case so the easiest group to consider is the group SO2n. It is in fact neither simply connected nor adjoint. So the simply connected group is the double covering of SO. This is called spin 2n. And there is also a joint group which is SO2n mod plus minus 1. So there is a double covering here and a double covering here. So altogether between the simply connected and the adjoint case, there is a covering of degree 4. And if I remember correctly, the Galois group of this covering is Z2 mod Z2. So you can find 3 intermediate groups in this case. One of these is SO2n, and there are 2 others. Also this similar picture can be given in the exceptional cases. So the discrepancy between, for instance, the degree of the covering map between the simply connected and the joint group in the type E6 is 3, in the type E7 is 2, and in the type E8 is 1, and so on. But what I want to point out is that there is a certain possibility of choice of a group in a given Dynkin type, and as we will see a bit later, the simply connected choice is the most convenient for many purposes. But on the other hand, the groups we are accustomed to, the most classically looking groups like SL, SO, SP, SO, sometimes they are simply connected and sometimes they are not. So sometimes if you want to have a group with a more with better properties, sometimes you have to go to the simply connected covering of the group that you have. Okay. Also, I should point out that whenever you have, so assume that G and G prime are 2 groups of the same type. So, for instance, G is simply connected and G prime is not. Then there is a morphism between them, which is a finite covering, and there is a one-to-one correspondence between parabolic subgroups in G and parabolic subgroups in G prime. And actually, it is just given by image or pre-image under this map. And the corresponding homogeneous spaces are just the same. So if you take a parabolic subgroup P in G and the corresponding parabolic subgroup P prime in G prime, then the corresponding homogeneous varieties are the same. So if we are just interested in homogeneous varieties, then we are free to choose which group among these possibilities to consider. And as I said, the best choice is the choice of the simply connected group. Okay, so what about the parabolic subgroups? maybe first we need to consider Barrel. So maybe let me tell you how do they look in these classical cases. So this will be a group. We will have a group here, group G, and here we will have its Barrel subgroup B. So how do Barrel subgroups in all these groups look like? So for instance, if you take the group SLM, then the most classical choice of a Barrel subgroup in it is just given by upper triangular matrices. So you can consider upper triangular matrices that have determinant 1, then this will be a Barrel subgroup in SLN plus 1. Again, there is no much difference in which group we consider the Barrel, because we can always go, for instance, to a group of simply connected type by taking the preimage of Barrel. So let me consider here the more classical case of SO, and also here. So these groups are not simply connected, but still, if we describe Barrel subgroups in these groups, then this will give you a description of Barrel in all other groups as well. And so, in fact, the description is more or less the same in all these types. The point is, there is of course a certain subtlety, because what is the special orthogonal or symplectic group? So this is the group of transformations of a vector space which is endowed with a non-degenerate quadratic or symplectic form, and which preserve this form. And if we want to understand how elements of this group look as matrices, so the result will depend on the choice of a basis. It will depend on how the corresponding bilinear form looks in this basis. And in fact, the best choices here is to take the bilinear form to be diagonal with respect to the opposite diagonal, and then in this case the Barrel subgroup also will be given by upper triangular matrices. You will just have to intersect them with a subgroup of matrices that preserve the corresponding form. So in some sense, you can always think of the Barrel subgroup as of the group of upper triangular matrices. This is literally true for the group SL, and this can be made to be true for other groups by appropriate choice of the basis. But the more important thing is what is the corresponding homogeneous space. So as we discussed, for any parabolic subgroup, we have this quotient G mod E, and a parabolic subgroup means that it contains a Barrel subgroup. So in particular, Barrel subgroup is parabolic. So you can ask me what are the corresponding homogeneous spaces for this parabolic, for these Barrel subgroups. Since Barrel is the minimal parabolic, therefore the corresponding homogeneous variety is the maximal compact homogeneous variety among all others. And in these cases, they can be explicitly described. So for SL, this is just the usual flag variety. So you consider a vector space of dimension n plus 1, and you consider all flags of one-dimensional, two-dimensional, and so on, n-dimensional subspaces, and G mod B in this case is just this flag variety. And clearly, you can see the connection between these two columns by noticing that upper triangular matrices is precisely the subgroup of SL that preserves the standard flag. Okay, so this is the variety G mod B in type AN. So in type BN, this is just the variety of isotropic flags with respect to our quadratic form, isotropic subspaces of dimensions from 1 up to n in the vector space of dimension 2n plus 1. So again, we have a vector space of dimension 2n plus 1, and we consider flags of isotropic subspaces of these dimensions, and this is G mod B in this case. For this symplectic group, this is very similar. So again, this time we consider a vector space of dimension 2n with a symplectic form, and we consider flags of isotropic subspaces of dimensions 1, 2, and so on up to n. And maybe the last row will look a bit strange. So here we have to consider only subspaces of dimensions from 1 to n minus 1 in the vector space of dimension 2n. And the reason for this is that whenever you have an isotropic subspace of dimension n minus 1 in a 2n dimensional vector space with a non-degenerate quadratic form, there are exactly two ways to extend it to an isotropic subspace of dimension 2n. So this means that we have to stop at this point. Okay, so these are the descriptions of the maximal homogeneous varieties of simple groups in classical types. You can also find some descriptions, for instance, in type G2 or in type E6. But I mean, in most cases, it is just enough to think about these varieties as about G mod B. In many cases, you don't really need a concrete description. And when you have a concrete description, it doesn't help you much. Okay, so this is about Borel subgroups. And now what about parabolic subgroups? So, in fact, as I already mentioned, if you fix a Borel subgroup in a simple algebraic group, then there is a finite number of choices for a parabolic subgroup that contains this Borel, and these parabolic subgroups are actually classified by finite subsets of the set of vertices of the corresponding Dynkin diagram. So they are in bijection with subsets of vertices. So the empty subset corresponds to the Borel. The entire set corresponds to the group G itself, which can be also considered as a parabolic in itself. Of course, this is not an interesting situation because the corresponding homogeneous variety is just one point. And there are many intermediate cases. And again, the most important cases are the parabolic subgroups that correspond to subsets of cardinality var, which means just vertices. So vertices of the Dynkin diagram correspond to what is called maximal parabolic subgroups. I mean, of course, they are not quite maximal because G is bigger, but they are maximal among interesting parabolic subgroups. And as I will mention later, if you are interested in exceptional collections on homogeneous varieties, G mod P, then the case that you really need to understand is the case of maximal parabolic subgroups, and all other cases can be reduced to this case in a certain way. So maximal parabolic subgroups are the most important and the most interesting, and so maybe let me tell you
Sasha, we have a question.
Yeah.
Does a maximal parabolic subgroup correspond to a vertex or the complement of a vertex?
That depends on your convention. I mean,
okay, so everything corresponds to G, though.
Yes. So the convention that I prefer is when maximal parabolics correspond to one vertex.
Okay.
Then everything should not correspond to G.
Right. So that's like this. Thank you.
Thank you.
So let me again pretend that this was an intentional misprint to check that people are alert. Okay. So as I said, maximal parabolics are the most natural, and to have for them meaningful notation, like, so if we have the vertex k, then we will denote by p sub k the corresponding parabolic. This is much more convenient than have a notation where the index is the complement of a vertex. Okay, so how do the parabolics and the corresponding how do these maximal parabolics and the corresponding homogeneous varieties look like in these classical cases? So for a cell, this is very easy. You just need to take upper triangular block matrices. I mean, two by two block matrices which are upper triangular. So here K corresponds to the sizes of blocks being being K and n plus 1 minus K. And the corresponding homogeneous variety is the usual Grassmannian. So this is just Grassmannian K n plus 1. So this is what do we have in type A. So in type B, we have a very similar picture, but this time we will have 3 block upper triangular matrices, and the blocks will have, I mean, again, in appropriate basis, it will look like this, and the sizes of the blocks will be K, K, and 2n minus 2k plus 1. And the corresponding homogeneous variety will be isotropic Grassmannian for this quadratic form of k-dimensional subspaces. In the symplectic form, in the symplectic and even orthogonal case, the picture will be quite similar, so I will not repeat it. And the corresponding homogeneous varieties will be isotropic symplectic, isotropic Grassmannian of k-dimensional subspaces, isotropic for the symplectic form. And here we will have, here the situation again is more complicated. So it is orthogonal Grassmannian k to n, isotropic Grassmannian, when k is at most n minus 2, and when n equals, when k equals n minus 1 and n, you should consider the following. So you can consider the isotropic Grassmannian of n-dimensional subspaces, and it turns out that it has 2 connected components. I will denote them, I will distinguish them by putting the sign plus or minus as a subscript here. And so one of these connected components corresponds to n minus 1. So this is n minus 1 and this is n. So these two correspond to the two connected components of this orthogonal Grassmannian. So this is how it looks, and so these are actually the varieties that we will consider. Okay, so some of these varieties we already discussed yesterday, namely the projective spaces. Yeah, so the projective spaces, in fact, they can be realized, they appear in this classification in two cases. So first of all, if we consider the type AN and the group P1 or the group Pn, then the corresponding G mod P is just Pn. And I mean, in one case it is Grassmannian of one-dimensional subspaces, which is clearly the projective space. In the other case, it is the Grassmannian of n-dimensional subspaces in a vector space of dimension n+1, which is just the projectivization of the dual vector space. So it's also Pn. And also they appear in type Cn for the parabolic of type P1. In this case, G mod P is again a projective space of odd dimension, e to n minus 1. So you see that odd dimensional projective spaces appear in this picture two times. Once as a homogeneous variety of groups of type A, and also as homogeneous space of groups of type C. We already know that in these cases there is an exceptional collection. Exists. And in fact, as we will see, a full exceptional collection can be constructed on many other homogeneous varieties of this type. And there is a big conjecture that I want to state now, which tells you that this is always the case. So big conjecture. For any G mod P, there is a full exceptional collection in the derived category of G mod P. So it's hard to say who is the person to which this conjecture should be attributed. Definitely it was discussed after works of Kapranov long ago, but I think it was it has never been stated in this form. So unfortunately, there is no nice name to write after this big conjecture. But let us hope that at some moment this will become a theorem, and then it will carry the name of the person who will prove it. Okay, so this is the big conjecture that we are going to discuss. Let me tell you in which cases it is known. As I said, it is known in a number of cases. Let me give you a brief survey. Okay, so first of all, as I mentioned before, it is known for the groups AN with the parabolic P1, AN with the parabolic Pn, Cn with the parabolic P1, because these are just vectors, projective spaces, and essentially it was proved by Beilinson. I think it was in 70s. Yeah, so I think this was in late 70s, maybe 78 or something of this sort. Okay, so this is the first case. The second case was proved by Kapranov, and it was 10 years later. So actually Kapranov constructed and described a full exception collection on AN in type AN for any parabolic subgroup, for any P. So this is Kapranov, and I think this is late 80s. It was actually his thesis. Okay, and beside this case, he also discussed, he also constructed exceptional collections on all quadrics, and these quadrics appear here in a number of types. So it is Dn P1. This is also Dn P1. This is also, I mean, there are some also sporadic cases which are also quadrics, so B3, P3, for instance, or D4, P3, or D4, P4, and also actually G2, P1. So all of these homogeneous varieties are quadrics. And in this case, also exception collections were constructed by Kapranov. Okay, after that, there was a number of series of examples where exceptional collections were constructed. For instance, you can take Bn P2, Cn P2, and Dn P2. So for the first two series, an exceptional collection was constructed by myself, and in the last case by myself and Maxim Smirnov. So in the case, this last case appeared very recently, only in this year. So it's actually this case is much harder than the previous two cases. And I think the last series is Cn Pn, which was in this case an exceptional collection was constructed by Anton Fonaryov. I think it was in 2019. And also there was a number of sporadic cases. So like maybe let me list some of them. So maybe I should list C3, P3, C4, P4, and C5, P5. Of course, these cases are covered by the result of Fonaryov, but they were proved before that by Samokin and Polishchuk. Also, there was so maybe I think we will not need these linking diagrams anymore. So let me erase them. There were also cases like C4, P3. So this was recently proved by Guseva. And also C5, P3, it was recently proved by Novikov. And I should also say that there was also in the case E6, P1, this was proved by Beilinson and Kapranov, and that happened maybe 10 years ago or something of this sort. And a very recent result, F4, P4, that was very recently proved by Beilinson, myself, and Smirnov. So you see the number of cases when the existence of a full exceptional collection, and actually the construction of a full exceptional collection is known, is quite big, and so it is very natural to expect that the conjecture is true in general. And also there is one more result that I would like to mention, that gives you yet another justification for the conjecture. This is a result we obtained with Polishuk some time ago. Actually, so this is a theorem. So actually, what we did, we suggested a uniform construction of exceptional collections of expected length in all classical cases. For types A, B, C, D, and all K. There is an exceptional collection of expected length. In fact, if a projective variety, if a smooth projective variety has a full exceptional collection, then the length of this collection is equal to the total dimension of the cohomology of this variety. So you always can expect what should be the length. But even if you manage to construct such an exceptional collection, it is, I mean, you still have to prove that it is full. And this is a hard problem, as I said yesterday. And for these collections that we have constructed, we don't know how to prove that they are full. So fullness of this is not known. So there is a general construction, but there is no proof of fullness of this exceptional collection. So if one would manage to prove that these exceptional collections are full, then this will cover all infinite series in the classification, and after that only a finite number of cases will have to be considered. Okay, this is general results known about full exception collections. Let me also tell you a couple of, an important observation that leads to various reductions of the problems of constructing exceptional collections. So this is an observation by Polishuk. He proved that if E is an exceptional object in D of G mod P, and G is simply connected, then E is G equivalent. So every exceptional object is automatically equivariant with respect to the simply connected algebraic group that acts on this homogeneous variety. So this helps very much if you try to construct exceptional objects or exceptional collections, and I think we will discuss how this could be used tomorrow. And today, let me tell you what are the reductions that can be proved by using this observation. So the first corollary from this theorem of Polishuk is the following. So assume that we are given a principal G bundle over some scheme X, where G is assumed to be simply connected, and let us consider let Y be the corresponding vibration with fiber G mod P. So this is just this principal bundle times G mod P, and you should take the quotient by the action of G that acts on G mod P naturally, and on the principal bundle also it acts naturally, so we can consider this G mod P vibration over X. So this will be locally trivial in Untitled topology G mod P vibration. And then if so I assume that G is simply connected. Then if D of G mod P has a full exceptional collection, so I will abbreviate this to phi EC. So if it has a full exceptional collection, then the derived category D of Y has a semi-orthogonal decomposition with all components equivalent to D of X. In a sense, for any exceptional object from this exceptional collection, using its equivalent structure, you can construct an object on Y that will restrict to each fiber of this vibration as the corresponding exceptional object, and this collection of objects will give you this semi-orthogonal decomposition. This semi-orthogonal decomposition will be just the relative version of your exceptional collection for this vibration. And in particular, if also D of X has a full exceptional collection, then D of Y also has a full exceptional collection. Just because whenever you have a semi-orthogonal decomposition with components, each of which has a full exceptional collection, then you can take the corresponding exceptional collection in every component, and altogether they will give you a full exceptional collection in the ambient category. So this is a very nice application of this observation of Polishuk. And for instance, you can apply this to reduce the question for G mod P where P is not maximal to the maximal case. So actually, for any, maybe I should write it before the corollary. So actually, any G mod P can be written as a tower of vibrations with fiber, of vibrations of this form with fibers Gi mod Pi, where Gi are some smaller simple algebraic groups. And so the corollary is if D of Gi mod Pi has a full exceptional collection for each I, then D of G mod P also has a full exceptional collection. And again, what you do, you just apply the previous corollary several times. Okay. For instance, since we already know a number of cases when a full exceptional collection exists, we can combine the knowledge of these cases with this corollary to deduce that if we take, so if G is of type AN, B2, B3, C2, C3, C4, D4, and G2, then for any parabolic, the corresponding homogeneous variety has a full exceptional collection. Just because for these groups and for all possible steps of this tower that can appear in these cases, we know full exceptional collections. And maybe one more corollary of this sort that I would like to mention is the following. So we can also discuss not G mod P for any parabolic, but say G mod B for the barrel. And again, in a number of cases, one can construct a full exceptional collection, namely if G is of type A, N, B, N, C, N, D, N, E6, F4, and G2. So essentially in all types except for E7 and E8, then the variety of full flex G mod B has a full exceptional collection. For instance, in the case E6, so the known case corresponds to this vertex, and if you consider the corresponding vibration, then one floor of this, if you consider the corresponding tower, then one floor, the bottom floor of this tower will be E6 mod P1, and the other floors will come from the remaining part of the Dynkin diagram, which has Dynkin type D5, in which case we already also know enough. And this is how it looks in general. As soon as you have, as soon as you know at least one G mod P for some maximal parabolic, you can reduce the equation for the full flag variety to simpler groups. Okay, so let me also mention another conjecture of similar sort that was discussed for some time. Namely, there was an observation that in types AN and CN, the derived category of this flag variety in fact has a full exceptional collection consisting only of line bundles. So some people conjectured that the same should be true in any Dynkin type, that if you consider the variety of complete flags, then the derived category should have a full exception collection consisting of line bundles. And one of the reasons for this, to expect this kind of property is because, for instance, for this variety, the cohomology ring is generated by the first Chern classes of line bundles. So this statement about derived category would be a natural generalization of this cohomological statement. But in fact, this is not true. So let me inform you about this. For instance, for type G2, one can check that there is no such full exception collection. Consisting of line bundles. So in fact, you just cannot find a semi-orthogonal collection of line bundles of expected length, which is failed in this case. So, in fact, you can cook up many conjectures of this sort, but not all of them will be true. So, for instance, this very naturally looking conjecture is wrong. Okay, so I guess my time is over. Yeah, so let me stop. And tomorrow we will talk again about exception collections on homogeneous varieties. Okay.
Okay, well, let's thank Sasha for a beautiful talk. Do we have any questions? You're too good at explaining things. Everything is so clear.
Or too boring.
So,
No, not at all. Not at all.
so I have one question. So when you say you have one of the expected length, but you don't know it's full, that's because it sort of generates might generate a finite index subgroup or something in the K group?
No. If it has expected length, then it definitely generates the entire Grothendieck group. So the reason is that on the Grothendieck group, you have the Euler form given by the alternating sum of dimensions of extension groups. And if you compute it on an exceptional collection, it will be upper triangular with units on the diagonal. So its determinant will be 1.
Okay.
And this proves that it generates the Grothendieck group. So as soon as it has expected length. But this is not enough to ensure that it generates the category. So the point is that, of course, you can always extend an exceptional collection to a semi-orthogonal decomposition by adding one more component, which is just the orthogonal to all objects in your exceptional collection. And in this case, this component, this extra component, will be so-called phantom category. So it will be a nice semi-orthogonal component of the derived category of a smooth projective variety with 0 Grothendieck group. This looks weird, but this happens. There are examples of categories of this sort. And there is a very recent result of Yefimov, which proves that any category of this sort, in fact, can be embedded into a derived category that has a full exceptional collection, which is kind of counterintuitive, but this is what he proved. So you cannot rule out the possibility that such phantom category may show up. Also, probably I should say that the only 2 cases of homogeneous varieties for which you can disprove the existence of phantom subcategories is the case of projective line P1, in which case this is quite elementary, and the case of projective plane, which is a very recent result by Pirashkov, and this will be explained later today. So this is a very non-trivial problem.
Thank you.
Do you expect there not to be phantoms for these homogeneous varieties, or do you actually?
I hope there are no phantoms, but I mean,
But so if there is a phantom, that's still potentially consistent with the existence of an exceptional collection, just you've got the wrong one, or?
this is also possible, yeah. So as I mentioned, Yefimov proved that any phantom can be embedded as a semi-orthogonal component of a category that has a full exceptional collection. That means, I mean, it can sit in categories of this sort, yeah? So maybe, I mean, if you in the end encounter a phantom in the derived category of a homogeneous variety, it is possible that you just have chosen a wrong exceptional collection. Yeah, this is definitely possible. But I mean, I hope that there are no phantoms here. But I mean, phantoms are very, I mean, they are very counterintuitive, and they show up, I mean, they have properties you would never believe something can have. So, I mean, for me, the first surprise was the very existence of these phantom categories. And now this recent result of Yefimov is a second surprise. So who knows how many other surprises they will show. I don't know.
Right, do we have any other questions for Sasha? All right, well, let's thank Sasha again.
Thanks for attention.
Yeah, thanks again. That was great.